and the type, I believe it is the type 4 offshore wind power plant. This incident is happening in Germany. So you can see that although both the control of the wind power plant as well as MMC are quite simple and standard, but we still see a lot of control interactions and which will make the system becomes unstable and finally lead to the trip of the either the wind power plant or the MMC. And that is the focus of this lecture, that how we can analyze the stability of the whole system. I believe there are some other lectures also address the stability issues, and basically we have two main stability assessment methodologies. The most straightforward one is the time domain simulation. I think it is the easiest way to implement the stability analysis. You just develop model and put it into the software and do the simulation, and the result is also quite straightforward, because if you see the oscillation in the time domain waveform, it is, you know that of course it becomes unstable. But there is also a obvious disadvantage of this method, because the first is the lack of insight. As long as you see this oscillated waveform, you really do not know the reason why the system becomes unstable or what component. It is the MMC or the offshore wind power plant is the troublemaker, should be responsible for this stability problem. The time domain simulation will not tell you that. The second thing is this time domain simulation is a case dependent result. For example, even you can see this system is stable in this case. For another case, for example, this offshore wind power plant, the power generation from this offshore wind power plant is reduced from 1 per unit, for example, to 0.5 per unit. You actually do not know the system will be stable or not in that scenario. So in principle, if you want to check the stability in all the operating conditions, you have to run a lot of time domain simulation, which is quite time consuming. So that is two main drawback of this method. And another method is called the state space analysis. I don't know whether other lecturer has addressed this methodology. I would say this is a very good method, because if you use the participation factor in the stability analysis, it will directly tell you which component or even which loop control parameters will be responsible for this unstable operation. And that makes you quite easy to identify the troublemaker of this unstable phenomenon. But the critical problem is that if you want to develop a state space model, if you have to know every control details of the system. And that is not a problem for converter manufacturer, but that is a huge problem for the transmission system operator. Because of the confidential reason, the converter manufacturer will never deliver the control details to the transmission system operator. That is why this state space method cannot be used for this transmission system operator. So that is the reason in this presentation, I will focus on the impedance-based stability analysis, which basically is that you treated this MMC system as well as the wind power plant as a controlled voltage or current source together with its impedance. Please notice that this impedance includes not only the effect of the passive element like the filter cables, but also include the element of the different control loops, which I will address later. The benefit of the impedance-based method is for TSOs, because the impedance can be directly measured from the black box model. You do not need to know the control details therein, but this method is still applicable. But for manufacturers, and they have more detailed control information at hand, but still the impedance-based method can provide much more insight for stabilization of the system. For example, if you see the impedance have a negative damping feature, you probably know that there would be a risk in that frequency range. Then you can have some corresponding mitigation method to stabilize the system. So that is also have some benefit for manufacturers. So that is why in this presentation I will focus on the impedance-based stability analysis. And because this is quite introductory level of this courses, so I will also have a brief introduction of this impedance-based stability analysis. I know it could be quite quite intuitive if you are working on that topic, but if you are not, so but I think some of you do not have this background, so I think it would be beneficial to have this introduction. So what is the impedance-based stability analysis? I will try to explain in an intuitive way, but not that mathematical rigor. For example, here we consider this MMC as an ideal voltage source series connected to this impedance, and the wind power plant have a similar manner. And we consider this MMC impedance has representation of the resistor series connected with the inductor. I should say that it is just an example for intuition. It's not the real case. And also we assume that the impedance of the wind power plant has behave like a capacitor. Then how could we tell this system will be stable or not? I think that is quite straightforward, right? For this IRC system, we can directly know the system will be stable or not. For example, let's first plot the impedance of the capacitor in the frequency domain. You can see that it is a common knowledge this magnitude of the capacitor will decrease with frequency increases, and the phase angle of the capacitor will always be minus 19 degrees. And for this IR circuit, if this resistor is larger than 0, you can assume that this IR circuit in the board diagram have this profile, which in the low frequency range, the impedance has behavior of resistor, so its phase angle is close to 0, and in the high frequency range, the impedance is dominated by the inductive behavior, so the phase angle is close to 19 degree. And of course, we know that if there is any positive damping, for example, this positive resistor, the system will always be stable, which means this from the board diagram, we know that this phase angle of this magnitude intersection point, phase angle difference of this magnitude intersection point will be less than 118 degrees. And of course, in that scenario, we know that the system, the oscillation, if there are any, would be damped. And the fourth case, if there's zero damping, so we can imagine the system will be critical stable. So that means if there are some oscillations, so it will be sustained. When it is reflected in the board diagram, you can see in that scenario the phase difference at this magnitude intersection point will be equal to 118 degrees. And in the last case, if we assume there will be a negative resistance in the output impedance, of course, in that scenario, the oscillation will be amplified and the system will finally become unstable. And correspondingly, in this board diagram, we can see that this phase difference at this impedance magnitude intersection point will be larger than 118 degree. So that is to say, we can only check this phase difference of impedance profile at the magnitude intersection point is larger or smaller than 118 degree to assess whether the system is stable or not. But I have to emphasize again, it is a quite intuitive explanation of the impedance-based theory. It is not that rigorous. For more rigorous, you should check the relevant paper and textbook. But for this course, you have this basic understanding. I think that would be enough. Okay, based on this insight, we can know that if we want to avoid any instability issue, we would always wish that the real part of each impedance is larger than 0, which means that both the MMC impedance and the wind power plant impedance should have some positive damping. That means the phase angle of this impedance should be within minus 19 degree as well as 19 degree, because as long as you have some positive damping, this impedance should always behave either like inductive or capacitive. So that is to say, its phase angle should always be within that range. And if that condition is fulfilled, we call that this impedance is passive. And we could, for example, the impedance profile shown here, we can see that in this frequency range, highlighted in blue, this phase angle is within the phase angle of the MMC is within 19 degree and minus 19 degrees. So that means that there is no risk of unstable operation, because since both the impedance, the phase angle of both impedance is within that range, you can imagine that this phase difference at the magnitude intersection point will never cross 118 degrees, so the system will always be stable. But in contrast, because of the control dynamics, the real part of the impedance could be negative, which means that there are some control-induced negative damping. In that scenario, this phase angle will be beyond either 19 degrees or smaller than minus 19 degrees, which indicates some negative damping. We also call it non-passive region. And when we say there is a non-passive region in particular frequency range, we can foresee there could be some risk of this oscillation on instability, because it is possible that the phase difference of the impedance interaction is larger than 118 degree. So based on that intuition, you can see that the impedance method is quite straightforward, because it reveals a lot of information. So you just can take a glance of the converter impedance, you can identify the risk of harmonic instability. And also for transmission system operators, they can easily put a specification to manufacturers. For example, they may want this impedance, the phase angle of the impedance to be within 19 degree as well as minus 19 degree in all the frequency range, to avoid the risk of instability. So that makes the TSO can easily make some specifications. That is the power. That is the good point of the impedance method. You can easily put some specifications. So that is the basic of the impedance-based stability analysis. But here you can see I have introduced this method in a quite oversimplified manner. I assume that this frequency-dependent impedance have a LCR behavior, but you know that in practice it is not that simple. It is even questionable whether this impedance can be represented by a transfer function only. Unfortunately, the answer is no. I will elaborate it further. For example, here I show this control diagram of the wind power plant, which is basically the two-level inverter. You can see that it uses this AC voltage control to generate Q-axis current reference, as well as DC voltage control to generate DX current reference. So you can clearly see the asymmetrical DQ control dynamics. And this asymmetrical DQ control dynamics will make this impedance representation much complicated than a simple single input, single output transfer function. I will explain further why it would be that complicated. Because the impedance is basically categorize the relationship between voltage and current, right? So we just assume if there are voltage perturbation injected at the terminal, and let's see what will happen in the response of the current. For example, we consider that this voltage perturbation at omega p to be injected at the AC terminal of the converter, either it can be a wind turbine converter or the MMC. Then we transform this perturbation into the DQ frame, because you know that the control is normally implemented in the DQ frame. And from alpha beta to DQ frame, you know that this is a simple frequency translation. So that means the frequency in the DQ frame is that the omega p minus omega 1. Okay, first we consider a simple case that the control algorithm implemented is symmetrical in terms of DQ dynamics. If this control dynamics is symmetrical, we can expect the response the current response in DQ frame also have the similar magnitude in DX and Q axis, and its frequency is also omega p minus omega 1. So it is also the current response also form a circle. Then we transform back to the alpha beta frame. We can see this current response also at omega p. So basically here, if provided the control dynamics is symmetrical in DQ, as long as we inject a voltage perturbation at frequency omega p, the current response would always be the similar frequency. That means the single frequency in, single frequency out. And this phenomena can be fully categorized by a single input, single output transfer function, impedance transfer function, like what I showed in the previous slides. But please bear in mind, this conclusion is based on a pretty strong precondition that is control dynamics should be symmetrical in DQ, but that is not true, as I mentioned before. Assume if there are control dynamics is asymmetrical, then what would happen? The result would be the current response in DQ frame would be also asymmetrical. You can see that this current vector in dx and qx would not be the same length because of this asymmetrical DQ dynamics. You can imagine that would be the direct result. So this current vector will not form a circle anymore, and should be rather instead it would be formed as an ellipse. And for this ellipse, you actually can decompose this ellipse to a circle rotating in different direction. One is omega with omega p minus omega 1, and another frequency is the negative frequency, which is omega 1 minus omega p. Then you transform all these two frequency components back to the alpha beta frame. Actually, you result ended up with two frequencies. This component will end up with frequency component at omega p, which is the same as the input frequency. But you can see that there's another frequency component with frequency at omega 1 minus omega p. Then when it transfers back to the alpha beta frame, you just added the frequency omega 1 to do the frequency translation. You can see the resulting frequency is 2 omega 1 minus omega p. So you can see that if the converter control adopt the asymmetrical DQ and control dynamics, which is always the case in practice, as long as you inject the voltage perturbation at frequency omega p, you end up with the current response with two frequencies. And for sure, this phenomena cannot be described or categorized by a transfer function anymore, but instead it should be represented by a transfer function matrix. So which is shown here, as you can see here, because you can see that as long as you have one voltage frequency, voltage perturbation, this response would be two frequencies coupled with each other. And here I would like to highlight some common misunderstandings in this aspect, because you may hear a lot of terminology of positive sequence or negative sequence impedance. I would say that it is not that rigorous, because I just use a very simple example to illustrate this. For example, because we know that this perturbation frequencies could be any frequency. It could be that this perturbation frequency is larger than two times of fundamental frequency. In that sense, 2 omega 1 minus omega p is negative sequence component, and omega p is of course the positive sequence component. In that sense, you can see that we see this positive sequence coupled with negative sequence component. But there's also fully possible that the perturbation frequency is smaller than this two times of fundamental frequency. For example, when we are doing subsynchronous analysis, while the frequency range of interest is quite low, in that sense, this condition we could met. But in that case, you can see this both 2 omega 1 minus omega p as well as omega p. That means these two components are both positive sequence components. So in that scenario, we end up that two positive sequence components coupled with each other. We never see one positive sequence coupled with another negative sequence component. So that is to say, in that scenario, because these two coupled frequency components are both positive sequence, we can never define a positive sequence and a negative sequence in response to that. So that is to say, this commonly used positive and negative sequence impedance is not that rigorous and will cause much more misunderstandings and even lead to inaccurate stability analysis. Because if you always treated one component as a negative sequence component, you may somehow ignore these conditions. But this condition should be always considered in the stability analysis. So I would prefer to just terminology it as just like the stationary frame or phase domain impedance instead of positive and negative sequence impedance. So here I just show you clear example. If we inject 30 voltage, 30 hertz voltage perturbation at the AC terminal of the MMC, you can see clearly that the voltage perturbation only includes one frequency, but the current response you can see clearly from the time domain waveform. It includes multiple frequency component, and for the FFT analysis, you can also clearly show that this frequency response include two frequency components. And what I would like to emphasize here is that these two frequency components are both positive sequence component. There is no positive sequence component coupled with negative sequence component. That is should be clear. Okay, so as I said before, in that regard, if we consider the asymmetrical DQ control dynamics of the MMC, both this MMC impedance as well as wind turbine impedance should be represented by this 2x2 matrix, which with frequency, which categorize its frequency coupled dynamics. Then you may wonder this impedance-based analysis based on the CISO representation, single input, single output representation of impedance, is still applicable or not. I would say that it is still applicable, but the key part here is that you should take this frequency coupling term into consideration. I will explain later. For example, in this case, you still can have this impedance equivalent representation of the whole system, but please bear in mind this impedance here are matrix, not transfer function anymore. So you can still represent this block diagram of this circuit diagram, but you can see here both this impedance or the admittance of the wind power plant and MMC have the matrix representation, so it is the two input and two output with coupling therein. But you can see that, but we know that for any control system, we can always do some arrangement and combination of control loops. So in the end, we can still get this single input, single output form. So that means we can still, based on apply the single input, single output impedance-based stability criteria on top of that. But the only difference is that this single input, single output equivalent impedance, this impedance actually have consider the impact of this frequency coupling components. That is the major part I would like to highlight here. But of course, if you only focus on the high frequency stability analysis, for example, this if you see this oscillation in several kilohertz, which is mainly caused by the control delay, and this in this frequency range, this very slow outer power control would not have too much impact. So in that sense, you can somehow neglect this frequency coupling term because that is caused by the power control loop, but that does not have impact on the high frequency range. So that is why you can neglect it in a high frequency stability analysis. Well, that is all for this impedance-based stability criterion. In this part, I just would like to make it clear how this implemented for the CISO system and also for the MIMO system. What I would like to show here is that although the accurate representation of the MMC on the wind power plant should be a 2x2 matrix, but this CISO impedance-based stability criterion is still applicable. You just need to derive the equivalent single input, single output impedance of the MMC and wind power plant by taking into the frequency coupling terms into consideration. But before we implemented the impedance-based stability criterion, of course, we have to guess the impedance of the MMC and the wind power plant. So that is why we have to do the impedance modeling. So that is what I would address later in this part. At the beginning, I would say that this impedance modeling of this two-level voltage source converter is quite mature. The basic reason is that for the two-level voltage source converter, it has a centralized DC link capacitor. So basically means that we have this, although we have this, let's say, sinusoidal or 15 Hertz PCC voltage and current, we can always transform into DQ frame. In DQ frame, we can get this constant voltage or the current. And that is very easy to do the small signal modeling because we get the time invariant operating point in DQ frame. We can always do the linearization on top of that and get the small signal model of the two-level VSA in the DQ frame. That is quite mature. I would say it people doing this study for more than 40 years ago, and it is a quite mature topic. But the things actually becomes much more complicated when we come to the MMC. Why the things become so complicated? Because the MMC is not like two-level voltage source converter. Its capacitor is distributed in each submodules, which means that each MMC, each submodules have to buffer this the single phase oscillating power, which leads to a quite obvious capacitor voltage ripple. If you do the FFT analysis for the capacitor voltage, you can see that there are multiple frequency components. These multiple frequency components would lead to the circulating current as well as the arm current also have multiple frequency component, which means actually even we transform these variables into DQ frame, we still get the multiple frequency component. It's not like a two-level converter, two-level voltage source converter. We get the constant value, then we constant DC value, then we can do the linearization on top of that. But for the MMC, because each state variables always have multiple frequency component, we actually cannot find a DC operating point. So how we can do the linearization on top of that? That is a problem which confused people for many years. So that is the main question I will address in this part. But actually, I have to be honest, this part is quite complex and heavy in mathematics. I spent almost half of my 3-year PhD to figure it out. So I think it is impossible to clarify in this short lecture. So I just would like to give you some high level understanding without going into too much into mathematics. So the basic thing is that for the MMCs, each state variables are not DC values, but it has multiple frequency component. So the question here is that how can we get the linearized model based on this system dynamics without any DC component? Because we know that if we have the DC component, we can easily do the linearization on top of that. That is very standard in the textbook. But the case here is that we do not have this any DC component, but rather each state variables have multiple frequency components. The solution is that we use the methodology called the harmonic state space, which is illustrated in this PhD dissertation from MIT, which is originally developed for modeling the blades of helicopters. And this method can be directly used for this modeling of the MMC, because you can imagine this rotation of helicopter is also like this periodic signal, so it shares some similarities. So the basic idea is that although these signals are periodic, we can always do the Fourier analysis because of this periodicity of the signal. And for the Fourier analysis, this Fourier coefficient is constant. If we just focus on the relationship of Fourier coefficients of input and output signals, then we end up with a linear time invariant system, which is represented by the Fourier coefficients. So basically, it is kind of like that we ignore this time varying signals, time varying components, but just focus on the relationship of Fourier coefficients of input and output signals. But because you know that Fourier coefficients, although they are constant, but actually they already represent the full information of the original system. So by doing like this, we actually can get the linear time invariant representation, but that ends up with a huge matrix whose elements are this Fourier coefficient of the system. That is actually quite a high level analysis. If you want to go into deeper, there's a lot of work to be done in that aspect. But here I will not go into that. I will just directly show you the result. Because of this, we actually can also develop this impedance matrix of the MMC, as I said before, because it is represented by the Fourier coefficients. So it should end up with a huge matrix with different frequency coupling components. And I will show the comparison of how important this this internal dynamics or capacitor voltage ripple of the MMC would affect this impedance profile. Here we just consider the open loop control of the MMC. If we just neglect its internal dynamics, for example, we treat it as a two-level voltage source converter. And for sure, in that scenario, its open loop impedance is just like inductors, right? Because it is open loop control. If we if we will take a look of its impedance of AC terminal for two-level VSC, its impedance is of course just like an inductance here. But actually, if we consider this internal dynamics, let's say capacitive voltage ripple of the MMC, actually we can see that this very interesting, this impedance of the open loop impedance of the MMC in the low frequency range has a capacitive behavior. You can see that its phase angle is close to minus 19 degree, which shows a capacitive behavior instead of inductive behavior. That is a unique feature of the MMC, which is quite different from the two-level voltage source converter. So here we see the significant impact of internal dynamics. So that is why it is important to consider it. I have to say, back to 4 to 10 years ago, a lot of people just treat the MMC model as exactly the same as the two-level converters, which is quite unacceptable, because here you can see there are quite a significant difference in the low frequency range, which means the low frequency behavior or the subsynchronous behavior of MMC is quite different from two-level voltage source behavior converter. I will give you a much more straightforward illustration here is that we operate the MMC with the open loop control, then we directly connect this MMC with a inductive load. If we imagine this is not a MMC, it's a two-level voltage source converter with its inductive output impedance, then of course we will not see any problem by connecting inductive load, right? Because we have an inductive output impedance of two-level converter, two-level voltage source converter, and the inductive load of the inductive load, and two inductors series connected with each other. There, of course, will not be any problem in that scenario. But as I mentioned before, in fact, the MMC impedance has a capacitive behavior in the low frequency range. Then you connect inductive load, it will form a series LC resonance, and that is the case. You see that in the simulation result, you can see this low frequency oscillation, which is triggered by this LC resonance. But this oscillation can never be explained if you simply use a model of two-level source converter. Then you just see the two inductors series connected, which is each other. You may be very wonder why this oscillation will appear. So this part, I would say that I just go into a very brief manner because it is very complicated. But if you are interested, you are very welcome to look at my relevant paper and other relevant papers. Okay, so suppose in that case we have the model of the MMC, impedance model of the MMC, and we also have the impedance of model of the wind turbine. And the impedance model of the wind turbine converter is just the impedance model of two-level voltage source converter, which is quite mature. Then we can put them together to perform some stability studies. Here, I just give you some one typical case of the system of the possible risk of system instability triggered by the phase lock loop of the wind power plant converter. For example, you know that the phase lock loop is used to synchronize the wind power plant converter with the power grid, and actually it will bring some dynamics and possible negative dampings. For example, we consider that the wind turbine converter is operating in the inversion mode, which is basically that it generates power from DC side and to the AC side, which is always the case. In that sense, we know that during the steady state operation, the VPCC and IPCC has opposite direction because it is generated power to the power grid. Then we assume that there's a small voltage perturbation at the grid side. For example, after this perturbation, this VPCC is changed to VPCC1, and because of the phase lock loop always will be used to synchronize the current with the voltage, then the current will change accordingly to synchronize with this voltage. If we take a look of this change of VPCC and IPCC, we can see that they are in opposite directions, which means that this small signal impedance, which is defined by the change of voltage divided by the change of the current, is smaller than 0. You can clearly find here that this is a negative resistance introduced by the peer, which has some potential to lead to the unstable operation of the system. But of course, this is just some intuitive analysis, which is not that rigorous. For the rigorous analysis, you still need to develop the accurate model of wind power plant converter, as well as accurate impedance model of the MMC, and put them together to use the impedance-based stability analysis to see the final result. But here, I just would like to give you some intuitions. Of course, in the rectification mode, the things would be different, but since the wind power plant converter will never operated in the rectification mode, so I will not go into that condition. Here you can see the case study that I developed the accurate model of the MMC, which is highlighted in red shown here, and also this the blue line shown here is the impedance model of the wind power plant. You can clearly see that this, as shown in this blue line, this impedance of the wind power plant around 15 Hertz. This phase angle of this impedance is quite beyond 19 degrees as well as minus 19 degrees, which indicating that the wind power plant converter has a significant negative damping around the fundamental frequency. And this negative damping is exactly caused by the dynamics of the phase lock loop, as I explained before. So you can see that if we adopt a quite large bandwidth of phase lock loop, this negative damping, the frequency range of this negative damping is quite wide. Then you can see that it could lead to the possible unstable operation of the whole system. You can see that this phase angle of these two impedance intersection point is larger than 118 degrees, indicating the system should be unstable, which is also verified by the time domain simulation result. However, if we reduce this bandwidth of the phase lock loop to 5 Hertz, you can see this negative damping is still there, but the frequency range is shrinked, and that could be stabilized the system. You can see in that scenario, this phase difference at magnitude intersection point is less than 118 degrees, and the system now becomes stable. Okay, so in the end, I will briefly and very fast go through this impedance measurement, because we talk a lot about this impedance modeling, but that is not possible for TSOs, because you know that for TSOs, they do not have any idea or control details of these control loops because of the confidential reasons. In that sense, they cannot do the modeling, but instead they have to perform the measurement. However, the current measurement, impedance measurement is, which I would say the mature technique is represented in DQ frame. That requires an additional phase lock loop for the measurement, but this additional phase lock loop itself will introduce some dynamics which will jeopardize the measurement accuracy. Of course, you can minimize this effect by introduce a very low frequency bandwidth phase lock loop, but it will, on the other hand, increase the measurement time. Also, the result, the impedance also will be in DQ frame, which is not convenient for stability analysis, because we know that the grid impedance, for example, like an inductor, have a more simpler form in this alpha beta frame. So we say that why not we come up with some direct impedance matrix measurement in alpha beta frame without using any phase lock loop. So that is what we have development with the German transmission system operator Tenant. This impedance measurement toolbox, the unique feature of this toolbox is that it can directly measure the impedance matrix in the alpha beta frame without any phase lock loop and DQ transformation. And the features of this toolbox, it is because you know that for transmission system operator, they normally use PSCAD for simulation. So that is why we are using Python language to develop this software package, which is fully compatible with the PSCAD simulation environment. And it is also fully automated. You just need to input the parameters, then it will invoke PSCAD automatically and perform the measurement automatically. And as I mentioned before, it can measure the metrics in the alpha beta frame without using any PR and DQ transformation. And we are very proud that this toolbox has already used by tenant in their several commercial HVDC projects, and we got a very positive feedback from them. So here is just some basic result. You can see that this red line is theoretical calculate the maintenance metrics, and this blue dot is measurement results, and you can see they are matched quite well. And because, as I mentioned before, this frequency coupling is not that important in the high frequency range, so we just perform the measurement in a low frequency range up to 200 Hertz. And here I just like to show you the case studies use the measurement. Of course, we have this theoretical model which is dictated by the solid line, but for the transmission system operators, they can directly use our toolbox to do the measurement and perform the stability analysis solely based on the measurement result. You can see if this measurement result matches very well with the theoretical result. For that is to say this measurement result is quite accurate and confident to perform the stability studies. You can see that here in this measurement result shows the unstable operations of the system, and it is also confirmed by the simulation analysis. And also it is a stable case where the measurement result shows the stable operation of the system and is further confirmed by the simulation analysis. And we would like to now the software is under commercialization, and you can find more details in this through this link. And I believe the first version will be available in this year. And if you are in academia, we can our current idea is that we can have a basic version for free. So if you are interested, you can contact me or Xiongfei afterwards. Okay, so that is basically all my presentation. I first introduce some impedance modeling and highlight the challenge of internal dynamics and nonlinear time periodic dynamics, and also the basic idea is use the harmonic state space method to linearize the system. Then I introduce a little bit about the impedance-based stability criterion. The idea behind that, the seesaw equivalent impedance ratio can always be used just to take the frequency coupling terms into consideration. Then I show some case studies of how this impedance model method can effectively to predict the system stability. And in the end, I introduce the impedance measurement toolbox developed by us. So I think that's all from my presentation. Your questions and comments are very welcome. Do you have any questions?
Hello, Dr. Wu.
Hello.
Hello. Good afternoon. My name is Juan from the University of Warwick. And I have a question. You said that when you control the offshore MMC converter, you control the VD voltage and also the VQ voltage, but at the same time you also control the IQ current and ID current. So so what's your control strategy of the grid side converter of the wind turbine?
I know your point. You may think that for this offshore MMC, because it is control its current, it might conflict with the control target of this. Because that is the grid side converter of wind turbine also control its current. That is your point, right?
Yes.
Okay, I may answer this question in this way. For this offshore MMC, it is the primary control target is its terminal AC voltage, not the current. So this current, you can see that we do not have any fixed reference for this current. This current reference for the inner loop is actually generated by the voltage control. So that means we do not have this stiff control of the current here, because you can imagine this current reference will also be changed based on the power generation of the wind power plant, because primarily we only control the voltage, not the current. So that is why there would be no conflict here, because the current control here is solely for current limitation purpose, not to control the current to a predefined value.
Okay. So another question is that I saw your research mainly focused on the impedance analysis of the wind turbine and HVDC.
Yes.
Yeah. So why do you choose to linearize the system by calculating the eigenvalues to evaluate the stability of the wind turbine and the HVDC?
So you mean a status using a status space method?
Yeah.
Okay. Yes. That is a good question. But as I mentioned before, the status space method is also a very good method, and it has a very clear advantage. And I think for the converter manufacturers, which they know every control details of the MMC, both status space method and the impedance-based method can also be adopted. But you know that for in the real world, the transmission system operator, like for example, National Grid UK in England, when they are doing stability analysis, they actually have no idea of control details. They just receive black box model from manufacturer like ABB and Siemens. And because of this confidential reasons, Siemens and ABB will never tell the control details to National Grid UK.
Yeah.
Then in that sense, if they don't know the control details, they cannot do the status-based modeling and analysis. But for the impedance-based method, they can still use that methodology because they can simply perform the measurement at this terminal.
Yeah.
Then get the impedance profile and to do the stability analysis. That is why, in the end, I introduced this impedance tool, a measurement tool for this German transmission system operator tenant. In their application, they have no idea of control details, but they just use our tools to measure the impedance of the black box model and do the stability analysis.
Yeah, I understand. The problem is that if we use the toolbox, and we found that there is some subsynchronized oscillation between the wind farm and the HVDC. In order to like improve the oscillation, we should maybe make some changes of the controllers. Yeah. So in the application, you said that we don't know the specific parameters of the controllers. So how can we improve the controller?
Okay, I will briefly introduce the procedure here. Maybe, for example, I can go to that slides. For example, here you can see that this is the impedance profile from MMC and the wind turbine. Although it is theoretically calculated, but you can also obtain it from the measurement. And you actually from this two impedance profile, you perform the impedance-based stability analysis. You know the system is unstable. And as I said, the powerful of this impedance-based method it reveal much insight, because you can see here it is clearly that the wind turbine converter's impedance have a negative damping nature here because its phase is beyond 19 degree and minus 90 degree, right? So we know that in that case, this wind turbine converter is the troublemaker, not the MMC. So in that sense, the normally common procedure is that the TSO, the transmission system operator, will contact the wind turbine manufacturer, like the Vestas, Siemens Gamesa, something like that, to say, hey, you say your impedance profile have so much negative damping and makes a lot of trouble. Let's modify it. Then the Vestas, for example, will modify the impedance by themselves, then and go back to TSO again, and then we'll do stability analysis again. That is the normally procedure.
Okay. Thank you very much. Okay.
You're welcome.
Yeah.
Any more? question?
Hi, Heng.
Hi.
Can you hear me? I'm Chao.
Yeah.
And first, thank you very much for the excellent presentation. It's very inspiring. And I think that I may have a comment here is that when you are talking about the misunderstanding of the positive and negative sequence coupling phenomenon, here I wanted to say that in the existed researches, even they are using the positive and negative sequence, they didn't mention that is the coupling between the positive and sequence and the negative sequence is the coupling between the positive sequence and the negative sequence is using the S minus J to omega 1. So this is a difference. You know, I mean that this model, we still call it as a sequence model because we use it as a complex variable. You need to change it from the scalar value to the complex value. So it should be the sequence domain model. But I fully understand your point and agree with you that it's not the coupling between the positive and negative sequence, but it's between the positive and negative. The sequence should make a frequency shift, and the shift is S minus J to omega 1. So this is the two coupling. And if you encounter have some things like the omega p is smaller than 2 omega 1, then this frequency in the negative sequence, it will be minus. So for the negative, so it's positive. So there's two positive coupling. So I just wanted to say this is my understanding. But since this is not called as the phasor impedance, because phasor impedance is using the angle and the magnitude for the calculation.
Yes, I agree. But how to say, for our let's say when we are working on power electronics, actually we have the deeper understanding of this underlying mechanism. So I think it's not a big deal to call it positive or negative sequence or any other name, as long as we understand correctly. So I think the name is not that important if we fully understand, as you said. I agree. But you know, the problem is that it makes a lot of confusion to the power system community, because the sequence impedance defined in the power system community is exactly what I showed here. But you know that, as you also agree, that is not the case here. So although maybe a small group of researchers in power electronics community note that this negative sequence is not exactly the negative sequence defined in this power system textbook, but the power system engineer, or I would say even some power system researcher, they don't know this. So that's because we have a lot of dialogue with industry. I can see that makes a huge confusion and sometimes even cause some troubles and unnecessary time wasting in the stability analysis. So that is why we have to we think it is important to make this name clear. Otherwise, especially for the power system community, it is not that good.
Yeah. So what do you prefer to call this kind of impedance? Is it stationary impedance or?
Yes, it is just the stationary impedance.
Stationary impedance.
Or impedance in phase domain. I think that both of them are fine.
Oh, in phase domain, not in phasor domain.
Yeah.
Okay. Then that's more clear. Yeah. Okay. I get your point. Thank you.
You're welcome. So